About 50 million years ago, long before humans built the first mud hut, long before we figured out insulation, long before we invented air conditioning units that cost $400 a month to run, a six-legged insect with a brain the size of a grain of sand solved one of the hardest engineering problems in history: climate control. Not partial climate control, not keep it kind of cool in summer climate control. I'm talking about maintaining a near-perfect internal temperature, within 1 degree, while the outside world swings from freezing cold at night to scorching heat in the afternoon, every single day, for decades, with zero electricity and zero moving parts. And in 1996, one architect in Zimbabwe looked at what this insect had built, copied the principle, and erected a massive shopping center and office complex in one of the hottest cities in Africa, with no conventional air conditioning. Zero. None. The energy bill dropped by 90%. This building exists right now. You can fly to Harare, walk through the front doors, feel the comfortable air inside, and step back into the African heat. It's called the Eastgate Center. The architect is Mick Pearce. The engineering firm Arup, which still operates globally and publishes their work, was his technical partner. Today I'm going to walk you through exactly how termites solved this problem 50 million years ago, exactly what Pearce reverse engineered from their mounds, and then, the part everyone else skips, step by step how you apply these principles to your home, your off-grid shelter, your cabin, or your bug-out location. No engineering degree, no utility hookup, no HVAC service call. By the end of this, you'll understand something your heating and cooling contractor has zero financial incentive to explain. Stay with me. The problem. Termites we're solving. The specific species that cracked this problem is Macrotermes michaelseni, a fungus farming termite that builds those massive cathedral mounds you've seen in documentaries. These mounds stand over 25 feet tall. Some documented mounds push 30 feet. They are, pound for pound, the most structurally complex biological construction on Earth. The termites are not living in the tall spire. That spire is mechanical infrastructure. The colony lives below, in chambers extending 15 feet underground, farming a temperature-sensitive fungus called Termitomyces. This fungus needs to stay at 87 degrees Fahrenheit, 31 degrees Celsius, within 1 degree in either direction. Too cold or too hot, and it dies. 2 million termites starve. The entire mound architecture is driven by this single survival requirement. Here is the engineering problem they're solving every day. On the African savanna, daily temperatures swing from 45 degrees Fahrenheit at night, about 7 degrees Celsius, up to 104 degrees Fahrenheit during the afternoon peak, which is 40 degrees Celsius. A 59 degree Fahrenheit swing. Every 24 hours, year after year. Inside the mound, 87 degrees Fahrenheit, 31 degrees Celsius. Plus or minus 1 degree. No electricity, no pumps, no thermostat, no moving parts except air and geometry. That is the problem. That is the solution. The mechanism, how the mound actually works. I want to be precise here because a lot of wrong information floats around about termite mound mechanics, repeated in architecture magazines, TED-style presentations, even engineering publications. The old standard explanation was simple passive convection. Warm colony air rises up a central chimney, exits the top, cool air gets pulled in at the base. Clean story, mostly wrong. A biologist named J. Scott Turner at the State University of New York College of Environmental Science and Forestry, searchable and verifiable, spent years actually instrumenting live termite mounds in Namibia. He measured real-time airflow with functioning colonies present. What he found? The airflow doesn't simply flow upward in a steady loop. It pulses. It reverses direction at different times of day. The mound functions more like a biological lung than a passive chimney, breathing in cycles that respond dynamically to external conditions. The outer mound wall is thin and porous, full of tiny channels close to the surface. During peak daytime heat, solar radiation on the outer skin drives gas exchange through those channels, carbon dioxide out, oxygen in, while the thick inner clay core maintains thermal mass, absorbing surface heat slowly without transmitting it quickly inward. At night, the dynamics reverse as the colony's metabolic heat becomes the dominant warm source. Turner also documented that termites actively modify their mound's ventilation channels in real time, sealing passages, opening others. The mound has 2 million biological actuators constantly tuning it. What Mick Pearce translated into human construction was primarily 2 of these 3 mechanisms: thermal mass and chimney effect ventilation. The third element, termites micromanaging every air passage, cannot be replicated without expensive electronic sensor systems. But here's what matters. You don't need all three. Thermal mass plus chimney effect alone reduces energy load by 80 to 90% in the right climate. Pearce proved it at 333,000 square feet. What Mick Pearce actually built. Let me be specific about Eastgate because the scale matters. This is not a cabin or demonstration prototype. The Eastgate Center is a 333,000 square foot commercial complex, approximately 31,000 square meters, in the commercial heart of Harare, Zimbabwe. Shopping mall on the lower levels, 9 floors of office space above. When it opened, the largest commercial building in Zimbabwe, operating continuously since 1996. Harare sits at roughly 4,800 feet elevation, about 1,465 meters, with summer days hitting 90 degrees Fahrenheit, 32 degrees Celsius, and nights dropping to 60 degrees Fahrenheit, 16 degrees Celsius. That 30-degree daily swing is the thermal engine Pearce's design captures. The floor slabs throughout the building were poured significantly thicker than standard commercial construction. These heavy slabs act exactly like the thick clay body of the termite mound, absorbing heat slowly and releasing it slowly. 1 kilogram of concrete holds roughly 880 joules of heat energy per degree of temperature change. Multiplied across 333,000 square feet of floor, that's a colossal thermal battery running silently under every room. Every night, when Harare's temperature drops to around 60 degrees Fahrenheit, 16 degrees Celsius, large fans pull cool outdoor air through the building. This air flows through the interior and through channels built into the floor structure, physically cooling all that concrete mass. By the time workers arrive in the morning, every surface in the building has been pre-chilled. The thermal mass then acts as a heat sink throughout the day, absorbing heat generated by occupants and equipment, preventing air temperature from climbing. The building closes up during peak heat. The mass does its work silently. 48 chimney stacks, visible in photographs of Eastgate's exterior as tall projecting towers, create a continuous upward draft, functioning exactly like the vertical channels in the termite mound spire. Warm air rises through these stacks and exits at the top, creating a low-pressure zone that pulls air up and through the entire structure without a compressor running. Result: Eastgate uses approximately 10% of the energy a comparable conventional building would consume on climate control. According to figures Arup and Pearce have discussed publicly, the building's owners saved approximately $3.5 million in avoided air conditioning costs in the first 5 years alone. Pearce has spoken about this project in recorded lectures findable online, including the pressure he faced from conventional engineers pushing him to add a backup air conditioning system just in case. He held the line. The building opened. The physics worked. Why this knowledge isn't widespread? If this works, proven in a real building in a real city for 3 decades, why isn't every building built this way? Incentives and misaligned economics. The conventional HVAC industry represents hundreds of billions of dollars annually across equipment, installation, maintenance, and utility consumption. A building that cuts climate control energy by 90% is not a profitable long-term customer for any of those sectors. There's no financial incentive to promote passive design. There's also a developer-tenant misalignment. The person who builds a commercial space and the person who pays the utility bills for the next 20 years are usually different people. Developers optimize for lowest upfront construction cost. Thicker concrete slabs and engineered chimney stacks cost more to build than thin slabs plus a rooftop HVAC unit. The developer takes the cost hit, the tenant captures the savings. That misalignment kills passive design before it starts. Then there's regulatory friction. Building codes were written around conventional HVAC systems. Getting a permit for a structure with no conventional air conditioning requires extra documentation and conversations with inspectors who've never encountered the design. Most architects make the rational business decision to avoid that friction. None of this changes the physics. The mechanics of thermal mass and chimney ventilation are as reliable today as when the first termite mound was built 50 million years ago. The 5 principles, how you build this. Now we get to what matters. These 5 principles scale from a 400 square foot cabin to a 333,000 square foot commercial complex. Apply what fits your build. Principle 1, thermal mass. You cannot do termite-style passive climate control without thermal mass. Everything else in the system depends on a large body of dense material that absorbs heat slowly, stores it, and releases it slowly. The concept to understand is thermal time lag. An 8-inch rammed earth wall produces approximately a 10 to 12-hour lag. Heat hitting the outer surface at noon arrives at the inner surface around midnight, when outside temperatures have dropped and that stored heat radiates harmlessly into cool night air. Occupants feel the temperature of the mass, not the outdoor air. Exactly what the termite mound's clay body does. For any off-grid shelter, target a minimum of 8 inches of dense wall material: rammed earth, adobe, concrete block, fieldstone, or poured concrete. 12 inches is substantially better. If code or budget requires wood frame construction, add thermal mass inside, a 4-inch concrete slab floor, concrete block interior partition walls with filled cores, or large dark water containers on south-facing interior walls. Interior mass works. It doesn't have to be in the wall itself. Principle 2. Night flush cooling. If your climate has a meaningful temperature drop at night, 15 degrees Fahrenheit or more, you have access to free cooling every single night. At dusk, when exterior temperature drops below interior, open your structure to let cool air flow across all thermal mass surfaces. Cool air picks up stored daytime heat and carries it outside. By morning, your mass is recharged and ready to absorb the coming day's load. Simplest implementation: operable low vents on the upwind side, high vents on the opposite side. Cool air enters low, contacts mass, warms, rises, exits high. No electricity, no moving parts beyond vent panels. A more deliberate system routes night air through a subfloor plenum, a hollow channel beneath your slab, maximizing contact between cool air and stored mass. This is what Pearce built at Eastgate. Operating rule: open all vents at sunset, close 1 to 2 hours before outside temperatures begin rising. In most North American climates, open around 8 p.m., close around 5:30 to 6 a.m. You'll calibrate the exact timing within your first week. Principle 3. The chimney stack. Without a vertical exhaust channel, your thermal mass eventually saturates. Air temperatures climb when the mass can no longer absorb heat faster than occupants and solar gain generate it. The chimney stack prevents this by continuously pulling warm air up and out. The physics: warm air is less dense than cool air. In a tall vertical column, warm air at the bottom rises toward the top, creating a low-pressure zone that draws air in from below. Taller chimney, greater temperature differential, stronger draft. For a 300 to 500 square foot cabin, a single chimney tower 2 feet in diameter, rising 4 to 5 feet above the roofline, creates functional stack effect. Options: stacked concrete masonry units, clay flue tiles inside a wood frame, or large diameter insulated metal pipe with a rain cap. Material matters less than geometry. Tall, insulated outside, so interior air stays warm, connected at the base to the interior space. Critical: the air intake must be at the lowest point of your structure, floor level or below. Ground level air is cooler. That temperature differential between cool base air and warm chimney top air is what drives the draft. Include a damper at the base, a simple hinged plate on a rod, so you can throttle from fully open in summer to nearly closed in winter. Principle 4. Earth tubes for subterranean preconditioning. Ground temperature at 6 to 8 feet depth is essentially constant year-round in most of North America, typically 50 degrees Fahrenheit to 60 degrees Fahrenheit, 10 degrees Celsius to 15 degrees Celsius, depending on your latitude. Warmer than winter outdoor air, cooler than summer outdoor air. A free, continuous thermal moderator sitting just below your foundation. An earth tube routes incoming fresh air through a buried pipe before it enters your structure. In summer, outdoor air at 95 degrees Fahrenheit, 35 degrees Celsius, exits the pipe at 60 degrees Fahrenheit, 15 degrees Celsius, or cooler, a 35-degree drop with zero energy consumed. In winter, outdoor air at 20 degrees Fahrenheit, -7 degrees Celsius, exits pre-warm to around 50 degrees Fahrenheit, 10 degrees Celsius, before it touches your heating system. The earth does the work in both directions. How to build one. Select your pipe. Smooth interior HDPE, high-density polyethylene, in 8-inch or 10-inch diameter from plumbing or agricultural supply stores. Smooth interior reduces airflow resistance. Corrugated drainage pipe works in a budget build, but smooth HDPE is the right material. Depth and length, 6 to 8 feet minimum depth. For a 400 square foot cabin, 100 feet of 8-inch pipe is a solid starting design. If your site doesn't allow a straight run, L-shape or U-shape at depth works fine. Use sweeping curves, not sharp fittings. Slope is non-negotiable, 1% grade minimum, 1 inch of drop per 8 feet of horizontal run, sloping toward a drainage point at the low end. Air in a buried pipe drops moisture as it cools. Without drainage, pooled condensation becomes a mold source that puts contaminated air directly into your living space. A simple perforated section or collection sump at the low point eliminates this. Surface intake. North-facing, permanently shaded, fitted with coarse mesh to exclude rodents and a rain cap. You do not want solar radiation heating the intake before air enters the pipe. That defeats the purpose. Pipe outlet connects to your structure at or below floor level, feeding into the subfloor plenum your night flush system uses. Earth-conditioned air enters from below, distributes across the mass floor, and rises into the living space driven by the chimney stack above. In summer, this creates a complete passive cooling loop. Cool, preconditioned air enters low, picks up interior heat as it rises, exits through the chimney. The system runs continuously as long as there is stack effect, which there almost always is. Principle 5. Solar gain control. The final element termites manage instinctively is controlling when and where sunlight enters the structure. In winter, you want it. In summer, you need to block it. South-facing windows in the northern hemisphere allow maximum winter solar gain. The low winter sun angles deeply into them throughout the day. A properly sized horizontal overhang blocks summer sun, which is high in the sky, without touching the low winter sun. East and west windows are the thermal enemy in summer. Morning and afternoon sun enters at low angles, overhangs cannot block. Minimize east and west glazing. The overhang calculation. Summer solstice sun angle equals 90 degrees minus your latitude plus 23.5 degrees. At 40 degrees north, Denver to Columbus to Philadelphia, the summer sun angle is approximately 73 degrees. Tangent of 73 is approximately 3.27. A window 4 feet tall needs an overhang depth of roughly 15 inches to fully shade it on the summer solstice. Build to those numbers and your south windows automatically manage seasonal solar gain with no moving parts. Winter sun enters, summer sun is blocked. For east or west windows you cannot eliminate, exterior shade screens, open weave fabric that reduces solar transmission by 60 to 90% are your most cost-effective retrofit. Mount them outside the glass, remove in winter. Putting it all together, the complete buildable system. Here is what all 5 principles look like assembled into one coherent design. 400 square feet, off-grid, year-round continental climate. Orientation, long axis runs east to west, south face primary. Site on a gentle south-facing slope if your land allows. Improves cold air drainage at night and maximizes solar exposure. Walls, 12-inch rammed earth or double-width grouted concrete block. If wood frame is required by code or budget, add 4 inches of poured concrete interior partition walls or stack concrete block interior partitions with cores filled. Floor, poured concrete slab 4 to 6 inches thick with rigid foam insulation beneath it. Foam prevents winter heat loss into deep ground. Leave the surface exposed, tile or sealed concrete, not carpet or wood, which insulate it from interior air and destroy thermal contact. Earth tube, 100 feet of 8-inch smooth HDPE buried at 7 feet, entering below floor level through the north foundation wall. North-facing, shaded screened intake at the surface. Outlet at floor level connects to a simple plenum box distributing air across the floor space. Chimney stack. 1 central exhaust tower 3 feet by 3 feet in cross-section, rising 8 feet above the roof line. Outer face insulated to maintain interior draft temperature. Damper at the base adjustable from fully open in summer to nearly closed in deep winter. Glazing, primarily south-facing with calculated overhangs, roughly 15 inches for 40-degree latitude. High clerestory windows on the south wall carry winter light deep into the interior. Minimal openings on north, east, and west walls. Thermal zoning, sleeping area deepest inside the structure, surrounded by the most mass. Living and cooking spaces face south for passive solar gain. Utility and bathroom spaces buffer the north wall. Seasonal operation, late spring through early fall, open at dusk, close at dawn. Night flush charges the mass, daytime mass absorbs the heat load, chimney vents the excess. Late fall through early spring, close the chimney damper nearly shut, let south windows collect all available winter sun, supplement the coldest nights with a small wood stove. With this system, the structure maintains interior temperatures between 68 degrees Fahrenheit, 20 degrees Celsius, and 78 degrees Fahrenheit, 26 degrees Celsius, through most of a typical continental North American year without mechanical climate control. Extreme cold snaps and heat waves may require supplemental input, but the baseline load is reduced by 80 to 90%. The deeper lesson. The termite didn't design this by calculating thermal mass values or running simulations. It evolved this solution over 50 million years. Colonies that built better mounds survived and reproduced. Colonies with worse mounds starved. Evolution is a blind optimizer with infinite patience, and it's been running climate control experiments on this planet since before most vertebrate species existed. Mick Pearce didn't invent anything when he built Eastgate. He translated a solution that already existed. He paid attention to a different domain and asked whether the underlying physics would transfer. It did, completely. 30 years later, that building still proves the point every summer in Harare. This is what the best survival thinking actually looks like. Not invention from scratch. Translation of what already works.